There's a common belief in computer vision that transformer-based object detectors just cannot compete with the speed of CNNs like YOLO, and for a long time that was the case, but it's no longer the truth. The model that you see at the top of the chart right now is RF-DETR, a fully open source transformer-based object detector released by Roboflow. And last month, we actually rolled out a big release with 3 new model sizes, nano, small, and medium. And as you can see, RF-DETR Nano is beating YOLO 11 Nano by 10 MAP points on COCO dataset, while actually delivering faster inference speed. In this tutorial, I will take you through the whole process. I show you how to find the dataset, how to fine-tune the model, how to evaluate and deploy it, and all that for free, both in Google Colab and Roboflow Platform. Okay, enough talk about the theory. Let's get our hands dirty and train our very first RF-DETR model. We'll be doing everything in Google Colab, and as usual, you can find the notebook for this tutorial in our notebooks repo. All you need to do is scroll a little bit to find it, and here it is, the RF-DETR fine-tuning notebook. We click the Open in Colab button, and after a few seconds, we get redirected to Google Colab website. First, we'll set our Roboflow API key as a secret in Google Colab. We'll need it to download our dataset from Roboflow Universe and deploy our fine-tuned model later in the video. To get the API key, we click on My Account in bottom left corner, then Account Settings. Then, from the list of workspaces, and I have quite a lot of them, we select the workspace we are interested in. Then click API Keys. From here, we can generate a new API key or copy one of existing ones. Now we go back to our Colab, and in the left side tab, open the secrets section and paste our API key under Roboflow API key name. Now we run the first cell of the notebook to load the secret from Secrets Vault into Python environment. Next, we'll confirm that our notebook is GPU accelerated. Mine is running on NVIDIA L4 with over 20 gigabytes of VRAM. You probably won't need this much memory. You should be able to get away with 8 or 16 gigabytes depending on your dataset. All you need to do is set the proper hyperparameter values, and we'll talk about that in just a second. If, when running this cell, you see a message about the NVIDIA SMI command not existing or something along those lines, let me show you how to fix that. You need to click on Runtime, then change runtime type and select one of available GPUs. Then your notebook will get restarted, so you need to make sure to rerun all the cells we've run so far. And finally, we need to install our dependencies, RF-DETR, Supervision, and Roboflow. The RF-DETR package is what we'll use to train and run the model. Roboflow will pull our dataset from Roboflow Universe, and Supervision will help us to benchmark the model and visualize the results. When working in Google Colab, it's a good practice to run inference with pre-trained model before starting the actual training, just to confirm the environment setup was correct. Let's download a few images that we'll use to test our detector. Feel free to upload your own images if you wish. You can simply drag and drop them into the files section on the left. Here's the code that we'll use for inference and results visualization. We are using RF-DETR medium model. One of the cool features of RF-DETR is its use of multi-resolution training. This allows us to trade off accuracy for latency without having to retrain the model. In this case, we use a 640 input resolution, but if we need the model to be faster, we could drop the resolution to, let's say, 320, which would make it less accurate, but also a lot quicker. Lastly, just before we run the inference, we are calling the optimized for inference method. This will compile the model to make it run faster during the inference. The rest of the code is just supervision, which we will use to visualize the results. Importantly, we are not applying any non-max suppression here. That's a big difference compared to YOLO-based models. YOLO models work by dividing the image into grid and predicting multiple bounding boxes and class probabilities for each grid cell. This process naturally creates many duplicated detections for the same object, so NMS is a required post-processing step to filter them out and keep only the best ones. It's time to fine-tune our model and custom dataset. If you have your dataset already, feel free to skip this part. Just remember, to fine-tune RF-DETR, you need your dataset in COCO format. If you have your dataset in another format like YOLO or Pascal Vogue, you have two easy options. You can upload it directly to Roboflow, which will automatically handle the conversion for you, and then you can export in COCO format. Alternatively, you can use our open source supervision package to convert between formats programmatically. If you want to go that route, I highly recommend checking our supervision documentation. It has detailed guides and code examples to walk you through the process. I spent a bit of time on Roboflow Universe and found this dataset. It has over 8,000 images of drones in flight already annotated. I'll fork the whole dataset and assign it to one of my workspaces. Once the fork of the dataset is completed, I can create the first version of my dataset. I will use two pre-processing steps: auto-orient to standardize the pixel orientation of all images, and resize, setting the image size to 640 by 640 with a stretch. We won't use any augmentations. Contrary to YOLO models that often require massive augmentations, RF-DETR can match or even surpass their performance with almost none. Finally, we click Create, and in just a few seconds, we should have our dataset ready to go. Now I can just copy the URL of the dataset from the browser, go back to Colab, paste it here, press Shift-Enter, and after a few seconds, our dataset is downloaded to our machine. By the way, you can also generate the full download code in Roboflow UI. All you need to do is navigate to the right dataset version, then click Download Dataset. Here we specify the export format that we would like to use. Like I told you before multiple times, to train RF-DETR, you need the dataset in COCO format. We select Show Download Code, then click Continue. And after a few seconds, a download code will be generated that we can simply copy and paste. If we open the left tab once again, we can see our UAV dataset, and when we open the root directory of the dataset, there are three subdirectories: train, test, and valid. Each of these directories contains images and annotations.coco.json file. The train split contains data the model will actually learn from. The validation split is used during the training to monitor model's performance on data it hasn't seen and to tune hyperparameters. And finally, the test split is held out until the very end of the training to get a final unbiased evaluation of the trained model performance. Importantly, the RF-DETR Python package requires all three splits to train the model. If your dataset doesn't have three splits, don't worry, you can easily correct that within Roboflow Platform or locally using our open source supervision package. I've gone ahead and downloaded one of these annotations.coco.json files and open it up here in VS Code so we can take a closer look. The file is structured as JSON object with several key sections. The images section is a list where each entry contains information about a single image, like its file name, height, width, and unique ID. The categories section defines the object classes in your dataset. Each category has a name, like UAV, and unique ID. Finally, the annotations section is a long list of every single labeled object in the dataset. Each annotation includes the bounding box coordinates in X, Y, width, height format, the image ID it belongs to, and the category ID that links to the correct class. This structure allows us to precisely define every object and every image. Time to train the actual model. We'll modify the code slightly as I want to train the nano version of the model. I'll also set the epoch count to 30, the batch size to 32, and the gradient accumulation step to 1. We press Shift-Enter, and in just a few seconds, the training starts. You can open the right tab of the Google Colab, and as the training starts, the data is being loaded. We can see that the GPU memory is getting allocated. In my case, I need around 20 gigabytes of VRAM to fine-tune my model, but this can vary depending on the resolution of images, the number of annotations per image in your dataset, and of course, the values of your training hyperparameters. Speaking of hyperparameters, RF-DETR has over a dozen of parameters and hyperparameters, and as the model is training, let's use this time to explain some of them. An epoch is one complete pass through the entire training dataset. Setting this to 30 means our model will see every image 30 times. The learning rate controls how much the model adjusts its weights after each batch. It's a critical parameter for ensuring the model converges to a good solution. Set it too high and the model might overshoot the optimal solution and never converge. Set it too low and the training can become painfully slow or get stuck in suboptimal result. I use the default value provided by RF-DETR package, and if you want to use a custom one, pay close attention to how it impacts your training metrics. Batch size is the number of images the model processes in a single iteration. I've set mine to 32. A larger batch size can speed up the training, but requires GPU memory. A related parameter is the gradient accumulation step. This is a clever trick if you don't have enough VRAM for larger batch sizes. You can use a smaller one and accumulate gradients over several steps. So for example, a batch size of 4 and gradient accumulation step of 4 will result in effective batch size of 16. This flexibility is made possible because RF-DETR uses layer normalization instead of batch normalization. Batch normalization requires the whole batch of data to be in memory at once, while layer normalization doesn't have that constraint, which means you can train on hardware with less memory. There's also early stopping. This monitors the model's performance on validation set and stops the training automatically if it doesn't improve for a certain number of epochs, which is set by early stopping patience. This is a great way to save time and compute resources. And on the other side of the spectrum, there is resume parameter. It lets you continue training from previously saved checkpoint. This is useful if your training got interrupted for some reason, or if you simply want to continue fine-tuning model later on. Finally, there are monitoring tools. RF-DETR package supports both TensorBoard and weights and biases. These are powerful logging tools that let you visualize your training progress in real time. You can use them to track metrics like loss and MAP, compare different runs, and really understand what's happening inside your model as it trains. Okay, 3 hours later, the training is finally done. Now, if we look into our output directory, we'll find few different checkpoint files. So let's break down the purpose of each of them. First, you have checkpoint.pth. This is the most recent checkpoint saved at the end of last epoch. It contains everything, the model weights, optimizer state, pretty much all of it. So it's perfect if your training got interrupted and you want to resume right where you left off. You also see files like checkpoint 9 and checkpoint 19 and so on. Those are periodic snapshots of your training state. You can control how often they are saved with checkpoint interval parameter, giving you a safety net in case you want to roll back to earlier training stage. Now, for finding your best model, you have two key files, checkpoint best regular PTH and checkpoint best EM8 PTH. The regular one holds the raw model weights that achieve the highest score on your validation set. However, the EMA checkpoint is usually the one you want to pay attention to. EMA stands for exponential moving average and is a technique that creates a smoothed version of models' weights by averaging them across recent training steps. This process often produces a model that generalizes better and gives you a nice boost in performance. And that brings us to the final file, checkpoint best total PTH. That's the one you want to use for deployment. It's a lightweight, stripped down file that contains only the best performing weights, whether they came from regular or EMA model, and nothing else. It's optimized purely for inference. And speaking of deployment, before we evaluate the model, let's get those weights saved in Roboflow. All we have to do is call the model that deployed Roboflow method. We just need to pass our workspace ID, the project ID, the dataset version we use for training, and of course our API key to authenticate the upload. Once we run the cell, a link will pop up right in the Colab, and that will take us straight to our deployed model as soon as the upload is finished. Now that our model is fine-tuned and our weights are uploaded to Roboflow, it's time to evaluate our model's performance. I'm going to show you two ways to do this. First, we'll run a quick evaluation right here in the notebook to get the baseline score. Then I'll show you how to use Roboflow to get a much more comprehensive analysis. So let's start with the first method. The first thing we need to do is free up our GPU to make sure we have enough resources available, because our GPU's VRAM is still almost completely allocated from our training job. If we would try to load another model right now, we would likely run into out-of-memory exception. So to prevent this, I prepared a small utility function called cleanup GPU memory. We can use it to free up any resources by deleting any leftover object references, triggering Python's garbage collector, and cleaning PyTorch CUDA cache. Let's call this function, and as you can see in the right-hand tab, our VRAM usage just dropped to almost zero, which is exactly what we wanted. Now we are ready to load the actual model. Since we trained Nano version, we initialize RF-DETR Nano class and load our weights from the checkpoint best total PTH file. And with that done, you can see that our Nano model took up only about 200 megabytes of additional memory. With our model loaded, the next step is to load our test data using Supervision's detection dataset class. From here, we can simply loop over the test set, running inference on each image and storing the ground truth and model's predictions in two separate lists. The final step is to calculate the metrics using Supervision mean average precision utility. We create an instance of that class, update it with our data, and compute the result. And here it is. So that gives us our MAP, which is a great initial check. In short, MAP is a standard object detection metric that summarizes accuracy of the model into a single value. The higher, the better. If you would like to learn more about the MAP and how it's calculated, I linked a detailed blog post in the description of the video. But if you are looking for a more detailed analysis, you can use the evaluation tools built into Roboflow Platform. The platform calculates not just MAP, but also other useful metrics like precision, recall, F1 score, and it generates a confusion matrix to help you diagnose where your model might get confused. Since we already deployed the model, all we need to do is follow the link generated during the upload, click Runtime Model Evaluation button, and that's it. This might take a few minutes, so we'll come back to take a look at the results a bit later in the video. The last thing I want to show you before we close the notebook is how to run the inference with our fine-tuned model. Just like with the model evaluation, I'll show you two ways to do this. First, using RF-DETR package, and then with Roboflow inference package. Let's start with RF-DETR. We will use the model that we already loaded for evaluation just a few moments ago. And the inference code is almost identical to what we use for the pre-trained COCO model, with the only difference being that we are using image from our test dataset. When we run the code, you can see the result, 2 images with the ground truth annotation on the left and model's prediction on the right. We can pick another image just to be safe, and once again the UAV is detected correctly. Now for the second method. Any model that you upload or train on Roboflow can be deployed using the Inference package. We haven't installed this dependency so far, so let's do it now. I'm installing the GPU version of Inference, which is optimized to run on NVIDIA hardware. The installation might take a few minutes, so let's speed it up. Once the installation is completed, you might see a message about conflicting dependency version at the end, but that won't affect our demo, so let's just ignore it. Now we can finally load our model that we just uploaded to Roboflow Platform. To do this, we'll need model ID, which we can just copy and paste from the URL. It consists of project ID / model version. And after copying it, we go back to Colab, paste it here, and then call the getModel function. We'll also need to pass our API key to confirm that we are authorized to use the model. And after a few seconds, we are ready to run the inference. Our inference code here is, once again, nearly identical to the one we ran a moment ago, with the key difference being that we are using the inference package instead of RF-DETR. However, under the hood, the difference is quite significant, as the inference engine is no longer PyTorch, but NNX. Just like before, let's change the image to something else from our test dataset, run the code, and it works just fine. As I mentioned at the beginning of the video, you can train your RF-DETR model both locally as well as in Roboflow Platform. Every user, even those on free tier, get a certain amount of credits every month. And you can use those points for all sorts of activities in Roboflow Platform, including creating and hosting your datasets, running inference, but also training your models. To train RF-DETR in the Roboflow Platform, we need to create a new version of the dataset. I'm keeping all the configuration the same. We will apply auto-orient as well as resize to 640 by 640 with stretch, no augmentations. And once the dataset version is created, we can train our model. We click Custom Train, then select RF-DETR and click Continue. This time I want to train a small version of the model, so we click Small, choose to train from Public Checkpoint and click Start Training. Depending on the image count and the resolution, training can take several hours. Shortly after the training starts, we should be able to track the progress in the browser, and once the training is completed, you'll get an email letting you know about it. A few hours have passed and I got my email. That means that the training for RF-DETR small model is complete. This is a great chance for us to look at the evaluation results for both RF-DETR Nano we trained in Google Colab and the small model we just trained in the platform. To do this, we open our project in Roboflow and go to Versions tab. Here's the first version of our dataset and the deployed model we trained in Colab. Let's click View Model Evaluation and then Show Detailed Metrics. We can see the MAP results, both the overall average and the breakdown by size of detected objects. The most important ones to look at are the purple and blue bars, which show our main MAP scores. Below that, we can see how the F1, precision, and recall scores change as we adjust the confidence threshold. It looks like the optimum confidence value for nano model is around 46%. We can also play with the slider to see how the value of confidence impacts those metrics. Scrolling down, you can see the confusion metrics I mentioned earlier. In this case, it's a little bit boring. It only shows information for a single UAV class, but it becomes incredibly useful where your model is trained to detect more than one class. Now, let's quickly check the MAP for our small model. We go back to our versions, select the second one, and once again click View Model Evaluation and Show Detailed Metrics. we can see that the average MAP is more than 2% higher than for the nano model. That's pretty big boost, but it's understandable given the larger model and longer training time. The model on the platform actually trained for more epochs than 30 we set in Colab. From here, we can also play with deployed model right in the browser. We can test how it performs on images from the test set, just like we did in Google Colab. We can also run inference on different images and adjust confidence threshold. You can also drag and drop your own files or run inference directly from your webcam. And that's it for today. We went through the entire process of fine-tuning and deploying RF-DETR model. If you enjoyed the video, make sure to visit RF-DETR's GitHub repo and leave a star there. It really helps us to promote the project, and stay tuned because we are already cooking new models. Make sure to tag me under your demos on X and LinkedIn. I'm really excited to see what you build. And stay tuned for more computer vision content coming to this channel soon. My name is Peter, and I'll see you next time. Bye.